Hello everyone, Dr. Zia Tahir here. This video tutorial is solution to problem 1.18 from Mechanical Vibrations 6th edition by S.S. Rao and the same one from the 5th edition by S.S. Rao. In 6th edition, this problem 1.18 is on page 122 and in 5th edition, it is on page 93. So this is about finding equivalent spring stiffness. So the static equilibrium position of a massless rigid bar hinged at point O. At this point O, it is hinged and connected with springs K1 and K2 is shown in the figure, assuming the displacement resulting from the application of force at point A is small. Find the equivalent spring stiffness of the system Ke that relate applied force to the displacement x as F is equal to Kx. So this sort of problem can be solved by using equivalence of elastic potential energy, but because in this question specifically F is equal to Kx is being provided, so this problem will be solved by a different method using a static equilibrium condition and then using laws of static equilibrium. So free body diagram of the system can be drawn as, so let's say here is point O and then that F force is given a little bit displacement so that angle is theta. So when that angle is theta, the force is being applied at this point F is being applied here and then this displacement is x. And then for this spring K2, I am going to assume that the spring due to K2 is F2 and spring due to K1 is F1 and they are acting with both of these forces are acting at a distance of L by 2. So let's say somewhere here. So one force is acting and then one force is acting somewhere here. So now when this force is trying to rotate that bar in anti-clockwise direction, so it is trying to compress this spring. So the reaction from this spring will be, or the spring force will be upward, which is F1. And then again, what will happen here? So when this force is trying to move, rotate it in anti-clockwise direction, so then this part will try to compress that spring. So the reaction force F1 will be F1 will be downward. Sorry, this is F2. So that is the free body diagram of the system. So the assumption for this problem is angle theta is small. So sine theta is nearly equal to theta and cosine theta is nearly equal to 1. And it says there in the question so that the displacement, assuming the displacement is small, so then that theta is also small. So then this force F now can be resolved into two components because if that angle is theta, so then uh, if I draw a line perpendicular to the rod, so then that angle is also theta. So then this force can be resolved into two components, one perpendicular to the rod and one parallel to the rod. So one which is perpendicular to the rod is F cos theta. So that is a component which we are going to consider because that component perpendicular to the rod is responsible for any moment, and the other one F sine theta, so that is actually passing through O, so it's not going to produce any moment. So then F cos theta using that small angle theta or small displacement, so then it is nearly equal to F. So we are going to consider only the force, not the component. And similarly for that F2, so its component which is perpendicular to the rod, that one will consider and that will be using the same assumption that F2 and then here is F1. So these are the forces, and we will use laws of static equilibrium to solve this problem. Now, applying laws of static equilibrium, that is sum of all moments about a point zero. So I'm going to use here sum of clockwise moments is equal to sum of anti-clockwise moment and taking moments about point O. So then moment due to that force F, there is this moment about point O due to that force F is this one is anti-clockwise, okay, and due to that force F2 is clockwise and F1 is also clockwise. So then the forces simply multiplied by the distances, so that F is at a distance of L by 2 from O, F2 is at a distance of L by 4, and then F1 is at a distance of L by 2, L by 4, sorry, from the point O. Now the moments will be F1 times by L by 4 plus F2 times by L by 4, and that F is equal to F times L by 2. Now that F is given as, this force F is simply given in the question as KEX, and then these forces F1 and F2 using Hooke's law, F is equal to Kx. So if we are going to assume that the displacement for spring K2 is x2, so that displacement from this point to force is x2, and then this displacement, let's say this displacement is x1 and this displacement is x2. So based on that, so then the forces F1 that will become equal to spring stiffness of 2k into x, and that F2 that will become k into x2, x1 and then x2. So then we can substitute the values of forces in last equation. So after substituting the value of F1, which is 2kx1 into L by 4, and F2 is kx, and then F given in the book as kex, so then this equation can be written. Now, now these x values, they can be estimated using here rule here, S is equal to r theta, where r is the radius of rotation. So x1 can be estimated, although it is going to go like this one, that is basically curved in a curved form. So S is equal to r theta, and again by assuming that we have to take its component in the vertical direction, which will be the cosine component, and then cosine theta is equal to 1. So cosine component like will be equal to the same r theta. So using that expression, x1 will become equal to L by 2 into theta, x2 that will be L by 4 into theta, and then x1 will become x1 that will become L by 4 into theta, and then this x will become L by 2 into theta, and similarly x2 will become L by 4 into theta. So these values after substituting into the equation. So then substituting value of x1, x2 and x into the equation, so that will, like left hand side and right hand side, they are written in terms of L and theta. And then further it can be simplified. It can be simplified further because uh, this first term that has common as L square theta is common, the second term L square and theta is common, and the third term L square and theta is common. So then we can take some terms common from here. So after simplifying, it will become a quarter KL square theta plus 1 over 16 KL square theta, and then a quarter KEL square theta. So that is 1 over 8. And then from left hand side, quarter L square theta can be taken as common, and it can be quarter L square theta into KE, and then quarter L square theta is going to cancel with the quarter L square theta, and then half K plus a quarter K, it is going to it is written as 3 quarter K. So that is 3 quarter K is equal to KE. So then KE, that will become 3 over 4K. So this is solution, or that is equivalent spring stiffness of the whole system, which is 3 quarter K. Thank you very much for watching.